I'll be back in 1 second. Okay, sorry.
Sir, now can we allow the participants to get into the meeting?
I'm sorry?
Sir, can we allow the participants to enter the meeting? We've got a few of them in the waiting room.
Are you waiting for other people to join? Is that what you said?
Yeah.
Okay.
Can we admit them?
Oh, wait a minute. I don't see. I see. Maybe I have to hit escape and I don't
No,
see
sir.
where.
That's fine, sir. We will admit them. You
Oh,
don't
okay,
need to bother
sorry.
about that, actually.
Now, how do I get back to where I was? Okay.
All right, sir.
Okay, thanks.
We'll start it in about 5 minutes.
Okay. Is my face centered on the screen pretty well? I can't see myself.
Well, not really, sir. It's at the bottom. So if you could rotate your
Okay.
camera a bit.
So it's about. So if I do that, is it better?
No, sir. It's even more low now.
The other way?
Yeah, the other way. A bit more.
Okay.
Yeah, perfect.
Okay, thanks.
So could you just rotate it a bit?
He is also the recipient of the Nobel Prize in Physics in the year 2012 for his pioneering works in the field of quantum mechanics. So, first of all, I'd like to invite my colleague, Ms. Nihla, to do the welcome speech. Nihla, please.
On behalf of Team Tathva, I would like to wish a warm morning to all our attendees today, and we hope that you're keeping well. Since its inception, Tathva has grown to become one of the biggest techno-managerial fests in South India through its efforts and the support extended to us by our parent institute, NIT Calicut. Once again, we're glad to have all of you here with us today. The lecture series has been the highlight of Tathva year after year, and joining us today is our esteemed speaker, Dr. David J. Wineland, the Nobel-laureate physicist, well known for making groundbreaking discoveries in the field of quantum physics. Dr. David J. Wineland is the Philip H. Knight Distinguished Researcher at University of Oregon and holds the Research Associate position at NIST and Adjunct Professor at University of Colorado. Having graduated from prestigious university like Harvard, he went on to design ingenious experiments to study quantum phenomena. His work is greatly advanced in the field of optics. Specifically, his research is on laser cooling trapped ions and using ions for quantum computing operations. In 2005, he has implemented the most precise atomic clock using quantum logic on a single aluminum ion. In 2012, he was awarded Nobel Prize in Physics for the experimental methods that enable measuring and manipulation of individual quantum systems. Today, Dr. David J. Wineland will be delivering a lecture on his topic, atomic clocks. Do join me in welcoming him to the Tathva lecture series. Over to you, sir.
Okay. Should I proceed?
Yeah.
Okay, sorry. Thanks for the nice introduction, and it's a pleasure for me to be here. It's Friday night my time and Saturday morning, I guess, for you. So quite a bit of time difference. So anyway, just to summarize briefly, I'm going to say, we're going to talk about clocks, but want to address why we need precise clocks. I'll give a little the idea of the basic ideas behind making an atomic clock, and if I do it right, you should be able to go out and make your own. These days, in the last 5 or 10 years, we now use clocks that tick at optical frequencies, and I'll say a little bit why that's interesting. And so throughout this, I'm going to give some examples using atomic ions that were from NIST, which is where I spent most of my career. But certainly neutral atoms are very good too. So the way it's just how we manipulate the atoms versus atomic ions is different, but the ideas are basically the same. And I'll try to, near the end, I'll try to give you an idea where the field is at and what might happen in the future. Anyway, for centuries, actually, precise clocks have been used in navigation. And I'm not a sailor, but for many centuries, the way people would navigate on the ocean, for example, is that the idea is basically to find where you are north-south, meaning where you are in terms of latitude. The basic idea, for example, in the Northern Hemisphere, it's common to look at the North Star and then measure the angle of the level ground where you are towards the North Star, this angle toward your view of the North Star. And that uniquely determines where you are in terms of latitude. So for longitude, the basic idea is just the same. The difference is because the Earth is rotating, you have to know the time to be able to interpret the angle to where you are in longitude, rather. So just to give you an idea of the errors that are if you don't have precise time, to get an idea of what errors in delta t in time give you in terms of this, that your length on the surface in terms of the Earth in terms of longitude. just as one example. Of course, the frequency of rotation here is 1 per day, of course, and the radius of the Earth is about 6,400 kilometers. So anyway, for an error of about 1 second, that gives a precision or uncertainty in the longitude of about 1/4 of a nautical mile. And there's an interesting, historical bit about this. And so apparently in the early 1700s, the British had suffered several naval disasters, and the reason was they just weren't able to tell where they were, and the ships would crash onto rocks and so on. So the British Parliament gave offered up a prize of £20,000, which was a huge sum of money in those days. And if someone could provide accuracy of 30 nautical miles, and that in terms of the rotation of the Earth or the position and longitude, that corresponds to an error of about 2 minutes. So but of course, this error had to be held for many months while the sailors were out to sea. So anyway, there's an interesting story that a British clockmaker, John Harrison, he finally satisfied the condition for the prize. And actually, there's a very good book. It's not very technical, but it gives a nice history of this story of John Harrison. And one thing that was kind of interesting, he satisfied the conditions of the prize, but then the Parliament kept holding back on giving on the prize, and finally the king had to step in to make sure he received his reward. So anyway, but I think most of us know that these days the modern navigation is done by satellites, and I'm going to give you a simplified picture here, but one of the basic features of the system is that the clocks should be synchronized. And the reason for that is if the clocks are synchronized, then an observer can find the distance that he or she is from the satellite just by by some simple protocol. And I'll assume here that, let's say the satellite emits a pulse of radiation every second tick. And of course, there'll be some delay before it reaches you on Earth, and so then the distance is just given by the speed of light times the time when it's the time when it's received versus the time when it's emitted. And so there's just a simple calculation here. If we can make time to about a nanosecond, that gives an imprecision of length of about 30 centimeters. And this is roughly where things are today in terms of satellite navigation. And another thing to say about a nanosecond per day is about an error fractionally of about a part in 10 to the 14. And this also represents the part in 10 to the 14th is about roughly the precision we need in frequency. That is, we need to hold the frequency, the tick rate of our clock constant to this part in 10 to the 14. So, of course, these days, that was a little bit simplified picture, but the GPS has a network of satellites. I forget how many there is. There's more than 4. And so the system is somewhat redundant. But so the clocks can synchronize themselves and then synchronize to a person on the Earth. And anyway, so that basically with a minimum of 4 satellites, you can get 3D position and time and so then, you don't have to see all the satellites, but if you see 4, that's enough to determine your position. So what about clocks? And I think, most, scientists don't think of clocks any different than the non-technical person. I mean, basically you need some periodic event and then a counter and then some mechanism that generates time. And so the traditional event generators are say the rotation of the Earth, of course, and then not just a couple in the order of 2.5 centuries ago. I mean, the pendulum clocks actually started to be very good, and they became very good in the last century. But now the atomic clocks do better. But it's amazing how good the pendulum, a carefully made pendulum clock could be. So what we're gonna talk about is atomic oscillations, and in some sense that acts just like a pendulum clock. And I'm not going to get very deep into the physics. You know, the classical model of electrons orbiting a nucleus is fine for the picture of a clock. Of course, since we're quantum physicists, the real picture is that, for example, if we have an electric dipole transition where the electron is oscillating back and forth, that sets up an oscillating electron density. The electron is not well localized. That's one of the key features of quantum mechanics, it's smeared out. But this oscillating electron density is like an electric dipole radiation. And that radiation can be picked up and, sorry. So I should want to say, though, that the other picture we have is these oscillations can be characterized as a superposition of two energy levels. The lower one I call 1, and the other upper one I call level 2. And this oscillating wave function occurs at a frequency that's equal to the energy difference between these two levels in the atom or the ion, divided by Planck's constant. So that's the basic frequency that we're interested in measuring. So actually the first accurate, or some of the first accurate atomic clocks were based on masers or lasers. And I think everybody knows what laser is: laser light amplification by stimulated emission of radiation. And it has the same meaning for maser. M just stands for microwave and L stands for light. So, but the operating principle is exactly the same. And in fact, the first devices working on the laser principle or maser principle was actually in the microwave. So anyway, one way these devices can be used as clocks is, first of all, I should say a little bit more about. So we'll have some mechanism that holds the atoms in place inside of a electromagnetic cavity, and the reason for the cavity is that the light bounces back and forth, and it allows as the atoms emit radiation, it allows the radiation to build up in intensity, and then we sample a small part of the light that's emitted. And so then the basic idea, after we get the maser or the laser running, we just simply count cycles of the radiation to generate time. And so a little bit of my personal background is, so when I started graduate school in 1965, and so I went to Harvard, and my thesis advisor, Norman Ramsey, who I show here, he's actually one of the most famous atomic physicists in the 20th century. And a little bit of the story is he and his colleague, Dan Kleppner, who went to MIT, he's not shown in this picture, but they had invented the first hydrogen maser, that is a maser based on the atomic hydrogen. And the energy difference there is kind of interesting. It's just, for hydrogen, it's the energy difference whether the electron spin and the nuclear spin are anti-aligned or whether they're parallel. And that gives a difference in energy so that difference in energy divided by Planck's constant is what gives the frequency. There's me in my younger days. See, I'm trying to get close to the boss there. But anyway, I got interested in just the kind of experiments they were doing. And so anyway, Norman, he as I say, he and his colleague invented the hydrogen maser, but they wanted to have accurate frequencies for all 3 isotopes of hydrogen. So my task was to build a maser based on deuterium. And a lot of the principles are the same. The only difference was the wavelength's quite a bit longer in deuterium. So that just took some special considerations to build the apparatus. And so this is the result of my thesis, that number there. And I think I'm the only one in the world that has that number memorized. But anyway, that was the result of my thesis. So it wasn't, as I say, it wasn't so, the techniques weren't so much different than the building the hydrogen maser. But I think doing this task for my thesis, I mean, it certainly, taught me about how to make control of the environment. And another interesting sidelight is these superpositions that is how long the atom radiates, is on the order of a second in the hydrogen or deuterium maser. As I say, the atomic oscillations are like the pendulum clock, but I showed, this is the exact same slide as you saw before, but there's a little bit of an issue. What I've shown here is right, but there's an issue that the atoms in the cavity are like two coupled oscillators. They're obviously the atom's not a harmonic oscillator, but it's still an oscillator, and they couple together. And the idea that what can happen is if the frequency of the cavity is not equal to the resonance frequency of the atom, then the frequency that's emitted by the cavity is not equal to the exact frequency of the atom. And there's ways to find out how to tune the condition where the atom and the cavity are the same, but they tend to be a bit hard to realize. So the more modern or common mode of operation these days for the accurate clocks is we'll have the atoms in some container. I won't go into too much of detail about that, but the idea is rather than having the atoms radiate, we'll start each atom in the lower energy state, and then we'll apply radiation to the atoms, which at a frequency which is near the resonance frequency for some time, and then the idea is if we just then measure the probability of excitation of going from the lower to the excited state, when that probability is maximum, then the frequency that we're applying with the laser or the maser or the microwaves is just given by the energy difference divided by Planck's constant. And then the basic idea is then to generate a clock, you just count cycles of the radiation source rather than counting cycles of the radiation from the atoms. So of course, one question: why atomic clocks? And the simple answer, they're just much more accurate than other clocks we know about. So just to give an idea to compare, I'm going to compare to a pendulum clock. That is the atom's atomic clocks to the pendulum clock. And they say, some consider it, it isn't exactly the same, but for example, similar considerations apply to, say, crystal clocks, since these are both mechanical. Anyway, I'll give you an idea how we compare to say a pendulum clock. And at first, for both cases, we have to consider the environmental sensitivity. And so for example, the rod that holds the pendulum, it might change with temperature. I mean, most materials, when the temperature increases, the length will increase, and of course that would then slow the frequency down of oscillation. And to give an idea of how well you can do that, a very low expansion material has a coefficient of a fractional change of length of about 10 to the minus 8 per degree C. And so this would then give, from this expression up here, would give a fractional uncertainty of about almost a part in 10 to the 8th per degree C. So that's temperature. Now we also have to worry about, I'm being very schematic here, but the masers actually, they would store atoms. In the case of hydrogen, they would store them in a glass cell. They would typically coat the inner walls of the cell with some non-stick material so the atoms wouldn't stick. And in fact, the hydrogen masers use Teflon so the atoms would bounce off rather than sticking to the walls. So we can think about the environmental sensitivity there. Now this is where things get really interesting, and actually the main effect of temperature in an atomic clock is due to Einstein, and basically what Einstein taught us about was relativistic time dilation. And of course, the profound thing that Einstein explained to us is that it's not that there's some mechanical thing about the atoms that changes, it's that time changes. In other words, time in a moving system goes slower than say we as a stationary observer. So we have to account for that effect if our atoms are moving, which in a cell like this, they're moving typically near the ambient temperature. Pardon me. So anyway, I won't go through this little calculation, but if we can figure out the fractional frequency offset given by this so-called time dilation shift. And for, I give it in terms of temperature and the atomic mass units, but for cesium, which has an atomic mass of 133, the change in temperature is about a part in 10 to the 15th per degree C. So it's almost 7 orders of magnitude less sensitive to temperature than a mechanical clock. And as I say, there's similar considerations come into effect for quartz crystal clocks. So let's see, whoops, sorry. So, and the other feature, of course, is what about reproducibility? So clearly for a mechanical device, in this case, the length of the pendulum would depend on manufacturing tolerances. And of course, critically, it depends on the local acceleration of gravity, which can change around the world. And finally, of course, there may be where the bearing that holds the pendulum bob may wear slightly, which will effectively lengthen the length of the rod. So that's some of the things that come in to play for a mechanical device. And the nice thing about atoms is basically all atoms of a particular kind are exactly identical. And this is verified, and it's almost at the heart of quantum mechanics. If they weren't identical, then you'd find it's different cesium-133 atoms running at different frequencies. So, but that's the key thing, is they're exactly identical. And atoms don't wear out as long as we can keep our cesium atoms in the cell long enough. We can use them forever. So, so there's some real advantages about thinking about atoms. So I mentioned the cesium example, and in fact, in the mid-1950s, precise measurements were done on the cesium hyperfine trends. It's exactly the same physics as I explained for hydrogen. It's the outer electron interacting with the spin of the nucleus. And anyway, so they were perfected pretty well in the mid-1950s. And this became the definition of the international definition of the second. So this was the definition of the second starting in 1967. And in fact, it's still the definition. There's, as you'll see, we can find much better clocks now, I think, but there isn't any big movement to change yet, because it's not clear what of the new clocks we have, which ones are best. So this remains our definition of the second. So we have to, any of them, when we do optical measurements, we have to refer back to the cesium frequency. Okay, so well, the other thing, and the other thing is what we're shifting to with. I gave you the basic idea. We apply radiation to the two-level system. And why? And typically those are at microwave frequencies, but we'd like to go to much higher frequencies, that is optical transitions, to define our frequency reference. And the simple reason for that is that the clock ticking rate is just much faster given by the frequency. So what I'm going to tell you is just one story that I was involved with when I went to NIST. And this is, we chose to work on mercury ions, and then we measured the frequency there is, about 10 to the 15 hertz. And the nice thing also about and this is true of other transitions in atoms and ions, is that for mercury, the absorption width, we can always absorb some radiation if we're not exactly on resonance, but it's given by this so-called absorption profile, and it's basically the width of this is given by one of the lifetime of the atoms in the upper state. But anyway, we can get very precise frequency discrimination with these very narrow line widths, and that's another reason why we go to optical transitions. Fractionally, we get much better resolution. So is our atomic clock or optical clocks a new idea? And certainly the answer is no. And interestingly, one of my colleagues back at at NIST in Boulder, which was then called the National Bureau of Standards. Anyway, he dug up some papers, and he found this text, which was written by Lord Kelvin and his colleague Peter Tape, and they attribute the idea to Maxwell, and that is that. And you can see from this, it's really what I've talked about here. They say, they talk about recent discoveries provide natural standards and in ready-made and infinite numbers, all absolutely alike, as I said. And so they had the basic idea there. And they said the time of vibration of a sodium particle, they were thinking of sodium rather than something else. But anyway, it applied to basically all atoms. And they talked about corresponding to one of the modes of vibration, and they were talking about optical oscillations actually. Anyway, and they say is known to be absolutely independent of the position in the universe, and probably will remain so for as long as the particle exists. And actually, this is the basic idea of the atomic clock. And the only problem with this statement here is if I highlight this phrase here is known to be absolutely independent of its position in the universe. And that's not true, but they can be excused because they didn't know about Einstein's theory of general relativity. And I'll come back to this idea in a little bit. So we're going to be using atomic ions, charged atoms. And I won't go into all the details. I'm sure, it wouldn't take me long to lead the students through how these devices work. But anyway, I'll just give you the highlights. Basically, the simplest kind of trap we have has 3 electrodes, and we apply a combination of static and oscillating electric potentials to these electrodes. And with these fields properly configured, we basically create a 3-dimensional harmonic well for the ion. So a simple picture of you can keep in your mind as a 2D analog of this is just like a marble in a bowl. And so anyway, the traps though were first developed starting in the late 40s actually, and by these guys. And in fact, Hans Stamelt and Wolfgang Paul, they shared the Nobel Prize with Norman Ramsey in 1989. So anyway, they were recognized for this development. So what I'm going to talk about is a particular this mercury ion idea, and I have to give first of all, you'll see our groups are real small. In fact, this is one of my long-term colleagues at NIST in Boulder. And anyway, so it was Jim Berquist here that led this project on the mercury ion. But anyway, so just to come back, so here's our mercury ion, and we're going to think about one ion in the trap. And in this case, if you're not familiar with it, this is just atomic notation, but for simplicity, we can call this level 1 and level 2 again. Anyway, the transition we choose here is an electric quadrupole transition, which has the upper state has fairly long lifetime of about 1/10 of a second. And so the radiation that excites this is in the near ultraviolet at about 282 nanometers. So why just single ions? And there is a reason here. So we think about this same trapping structure, and the problem is that these atoms, when the mercury ions are in the upper level, the electronic configuration, the spatial distribution of the electrons looks like a football. It's and it has a quadrupole moment. And the problem, And the problem with that is that if we just had 2 ions in the trap, the electric fields from one ion onto the other ion, they're inhomogeneous and they interact with this quadrupole shift. And for the typical conditions we were using, the shift was about a kilohertz, and we're trying to get down to a millihertz precision. So it's just hard to control this shift. And that's why we worked with, in the case of mercury, why we worked with one ion. So what about detecting? Now, if I just come back here, I mean, in principle, a lot of spectroscopy is done by, looking at absorption. We could look at the absorption of the decrease in radiation as it's absorbed by the atom. And the problem with for one atom, it's extremely hard. Actually, as an aside project, we just for fun, we did find a way to measure the absorption of a single ion, but it was a very cumbersome, difficult experiment to do. Anyway, get back to this slide here. Let's see. So how do we detect them? Absorption isn't very good. We just can't absorb much light. So the way we look, and this is a common technique in a lot of atomic physics spectroscopy experiments. Excuse me, is we're gonna think about a second transition, and in this case of mercury, up to this P level, and this transition here can scatter light at a very 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 high rate, and because the lifetime here is about only 2 or 3 nanoseconds, and whereas the lifetime of this upper state on the D level is about 1/10 of a second. So the idea here, though, is if the atom is in the ground state and we excite this transition there, and we can scatter a lot of light. So let's just say the way we're going to do is we're going to alternate the radiation, the clock radiation we call it, that tries to drive this transition, and then we turn that off and turn this detection light on. And so what happens is if let's say we start the atom in the ground state, and then if we apply the clock radiation, and the clock radiation isn't close enough to the absorption feature, then the atom remains in the ground state, and then we can see the scattered light when we apply the second laser beam. And in fact, we can scatter about 100 million photons a second, and we only need to capture a small fraction of those to get a good discrimination. Yeah, so that was the second part of what I say. When the atom is promoted to the excited state, then there's this transition doesn't play a role, and there's no scattering. And just to give you an idea, this is some data where, just to give the idea, we ran both lasers at the same time, and that when the atom was fluorescing strongly, that indicated it was in the ground state, and when there was very little light, then it was in the upper level. And in fact, the light that's there is just from scattered light, in the apparatus. And so we could basically, by setting a discriminator halfway up these curves, we could tell with 100% efficiency when the atom absorbs the light. And actually, we can see a single atom now. Well, we can't see mercury because it's in the ultraviolet, and our eyes aren't sensitive to that. So what we did is, we had a special video camera made, and it's not any more sophisticated to what you can buy in your department stores these days, or get in your cell phones. But anyway, this one required the detection of ultraviolet light, so we had to get a special one that would detect the scattered light from this ultraviolet transition. And in fact, we could, as I say, we can't see it with our eyes. The radiation, the frequency, the wavelength is too short. But we can with this video camera, we can actually see a single line. So it's kind of fuzzy. There's some scattered light from, light scattering off of parts of the apparatus, but seeing one atom is pretty clear, of course. And actually, another interesting side light of this picture here is that the size of the image of the atom here is actually about 500 times larger than the wave packet, which describes the size of the atom. We have different ways to tell the size of the atom wave packet, and in fact, so this is highly defocused. Was just limited by our observation optics. But anyway, the atom is really well. The ion in this case is very well localized by these fields. The other thing we realized this detection transition is that we can use it to slow the velocity of the atoms down, and it's called laser cooling popularly. And the idea here is not so. It's not very difficult. Maybe I can at least give you the idea that suppose the atom is moving against this laser beam. But let's suppose this light is tuned slightly below the frequency where the atom wants to absorb maximally. When the atom moves against the laser beam, there's a first order Doppler shift, which shifts the apparent frequency of the laser up such that it can be near the resonance frequency of the atom. On the other hand, when the atom moves in the other direction, it's shifted by the first order Doppler effect. It's shifted even farther away from the transition. So there's big differential in whether the atom is moving against this laser or the radiation or with it. And the idea is that when it's moving against the laser beam, it feels the momentum kicks more strongly from the absorption and emission, so-called radiation pressure. And we can use that differential effect to cool down the atoms, which is important for this time dilation shift that Einstein told us about. And actually, just to give you a rough idea, we for some of these early experiments in the mercury, the apparatus was at room temperature, and this is the temperature that the ion would come to, near room temperature. And this so-called radiation pressure laser cooling, we could lower the temperature of the atom almost by a factor of 1,000,000. And so this greatly suppressed this time dilation shift which was important later in our measurements. So this shows a picture a little later of our group. So the laser cooling experiments I did with my colleague Bob at drilling area first, and then we got together with Jim Berquist and later Wayne Atano, who is our resident theorist in the experiment, and we started working on this first of all this mercury ion clock, and this just shows some of the laser stuff around. This is a dye laser, if somebody remembers that for that. Anyway, so there's so many things that, so many details we had to figure out with this mercury clock. But just to give you some of the features we were able to employ is, first of all, the trapping basically gets rid of the first order Doppler shift, and that's mainly due to the fact that the atoms on average are not moving. They're held nominally in one place. And the laser cooling, as I say, can significantly reduce this time dilation shift. And also, by the time these better experiments are done, we typically we had the trap apparatus surrounded by liquid helium, and the reason for that was important. It was basically all the background gas inside the vacuum system would freeze to the walls, and so we didn't have to worry about shifts due to collisions of the background gas with the ion. And another interesting thing is that another one of the shifts we have to worry about is so-called black body shifts, and that's sort of a fancy name given to thermal radiation. That is the thermal radiation in the room. In fact, it's just funny to think about some of the numbers. The electric fields from the black body, this thermal radiation in the room is, for typical conditions like in your room and my room here, is about, the electric field is about 10 volts per centimeter. So it's not small, and that can shift the frequency of the atoms strongly. So this was one reason to do the cooling, is that this black body shift goes as the temperature to the fourth power. And so by going to liquid helium, then 4 Kelvin, we significantly suppress that shift. So the nice thing about this is a long story. We started this experiment and basically finished. Well, we went on to other things, but in 2005, then Jim Berquist and his colleagues got down in this paper here. They got down to where the uncertainty was about almost less than a part in 10 to the 16. And the significant thing about that is that this was demonstrably better than the accuracies of the cesium. And I don't know whether we'd want to say that signaled the generation of the era of optical transitions, but in a way it has. All the accurate clocks now are based on optical transitions. So I'm going to say a little bit more about frequency shifts. We talked about the shift, and we have to we have to worry about and thermal radiation. And there's other more mundane things that the vacuum systems are typically involve metal and glass, and they can get charged up to give electric fields, and also our stray magnetic fields due to currents in the apparatus. So we have to worry about these mundane things. And then there's quite some more interesting things are these fundamental effects. I've told you now about atomic, the time dilation due to motion, and how we reduce that by doing this laser cooling. And there's another shift though that Einstein told us about when he got to his theory of general relativity. What he told us was that basically time runs at different rates in different gravitational potentials. And again, it's you want to think about this. It's not that there's something changes about the atom. It's just time that changes, and that's the critical thing that Einstein, really a fundamental constant he brought out to tell us about. So this is kind of like a second time dilation shift. In fact, the atoms in a potential they run at lower frequencies than if they're free of a potential. And just to give you an idea of the shifts, the so-called, we call it a red shift, and that comes from astronomers because for distant stars and galaxies that are moving away from, the radiation has shifted from mid-range to red, and that's why it's called the red shift, because it's shifting the frequency down. But anyway, at the surface of the Earth, this expressed fractionally, this shift is about a part in 10 to the 9, and so this is much bigger than the frequency precisions we're getting these days. So we had to, we have to correct for that. And I think just so we can. One way we have to worry about this is that if we want to compare clocks, we have to worry about they may be at different heights, and we have to account for that. Anyway, it's a small effect, and just to get on a human scale, just how to illustrate that it's small, is a little story you can cook up is suppose you and your twin sibling were separated at birth, and you live at sea level, and your twin lives in Boulder, Colorado, which is about 1.5 kilometers above sea level. It turns out your twin will, after 80 years, your twin will only be about a millisecond older than you. So it doesn't affect us all in our ordinary day lives, but it's something we have to worry about in the clocks. So I'm just giving you an idea about this, just a little fun experiment I did with this gravitational redshift. So this is, we later switched to aluminum ions that had a couple of nice features. And in fact, I mentioned that the mercury ion had a 1/10 of a second lifetime. This had a 20-second lifetime of the upper state. And that made this absorption feature about 200 times more narrow than the mercury ion transition. And so these are the two Daves that were the main people on this project. And I call this an atomic clock. It doesn't look much like a clock, but just to give you a rough idea, a lot of this is optics for lasers, and there's some lasers hidden behind in the opposite end of the table in this shiny tube here. That's where the vacuum is and where we hold our small ion trap, and then we direct it through the light, the radiation through the windows in this apparatus. So anyway, just for fun, what we did is we called this clock number 1, and in an adjacent room is actually the room off to the right of this picture, next to this lab, and we made another aluminum clock, and we could measure the ratio of the frequencies, and we can do actually better than this, but this was. So they were equal to about a little better than a part in 10 to the 17. And so then what we did, that one of the guys working on this experiment, James Chow, you can see what he's done is he's stuck jacks underneath the table here, and he jacks it up and raises it up, and anyway, so we raise it up to about 30 centimeters. And then we compared the ratio of these two clocks, and it's not, as I say, we could do more accurately, but in a very short time, we could see that that this clock was running faster than the clock next door, since we had raised it by 30 centimeters. So it's kind of fun to do those, that kind of experiment. Actually, this thing about the redshift, I mean, it's really, you have to think futuristically, but let's suppose you were the king or queen of the universe, and you wanted to find the ultimate, the ultimate clock. Well, the problem is we have to worry about this gravitational potential redshift. And just to give you an idea, there's this galaxy cluster. I mean, it's incredibly far away, but it's also very massive. And the gravitational potential redshift from this galaxy cluster is about 5,000 times larger than the gravitational potential shift of a clock due to the Earth when it's sitting on the Earth. And so if you had to designate the ideal clock to be a standard, it almost, you can't do it, because these shifts you can't know precisely from these distant sources. So now for locally, for anything near the surface of the Earth, the change in the gravitational potential, or in other words, the change of the rate of time, is exactly the same for all systems, around the Earth. So we don't see the difference. We can't see the difference as we go from one side of the Earth to the other. Anyway, it's just something to think about, huh? Oh, this is what I just said. Yeah. So, I'm just going to say a little bit about, I've only talked about these ion examples, and there's many other platforms. There's lots of different ion experiments, first of all. But also the neutral atoms are extremely good too. And so one of the things that the neutral atom groups have done is they make what they call an optical lattice, and they make an arrangement of, for example, 4 intersecting standing wave laser beams, and they can in a two-dimensional picture of these so-called optical lattices, you can think of it kind of like an egg crate, and the atoms, if they're cold enough, will fall to the bottom of these and be localized. And so the nice thing about these optical lattice clocks based on neutral atoms is that it turns out that I don't have time to go into this feature, but the measurement precision, that is the error we get on the frequency measurement, scales as 1 over the square root of the number of atoms we're observing. So the idea there is that even though we can get the accuracies of the accuracies, that is the uncertainties due to things like environmental effects, are the same for both clocks. The nice thing about the neutral atoms is that they can just get a lot more atoms than we can in our ion trap. So they can measure these high precisions much faster than we can with the ions. So anyway, but just to give you an idea that I think for both the neutral atoms and the ions, that the uncertainties now, due to the fundamental shifts, we're down near the part 10 of the 18th level. And I'm putting up this one reference here. It's not obviously not real up to date, but if you want to learn more, I would go to this reference, because it features all these different devices, and some of the devices featured are much better these days. But this is a good paper to start if you're interested in reading more about these clocks. So what about the future? And you might say, well, now it's clear that the optical clocks are better than the cesium clocks. So, maybe we need a new standard besides cesium to define the second. And I'd say one problem is right now is that there's so many good, optical clocks. But the problem is there's no clear winner. So if we change the definition to be mercury or aluminum ions, let's say, which has this accuracy as well, then, but there may be a better clock with a different kind of atom that comes along next year. So I think people are going to be slow to change the definition. So right now the definition of the second remains based on the cesium transition. Anyway, but that'll eventually probably happen. But anyway, that's more of a science politics issue, not physics question. But anyway, So the other thing is, and this is a great topic by itself, we talk about making entangled states. This idea of entanglement comes from Einstein and his colleagues. We can make correlated states that some are called spin squeeze states. I won't go into it. I mean, I could explain this in another hour, Gideon and I, about what this is about. But the nice thing is that is that for these entangled states, the imprecision, whereas for atoms that aren't entangled, it scales as 1 over the number of atoms. But with these particular entangled states, it can go as 1 over the n. So you win with a large number, you win in terms of precision. Square root of n, fat, best, or better. So anyway, but this is still off a little bit in the future, but people are starting to think about both these for redefining a second and also using these so-called entangled states. So anyway, what's the future of clocks? And we still think about navigation, and now with the precisions we have with our clocks, we can think about navigating at the 1 centimeter scale, either by the satellite methods or by, for example, the gravitational potential redshift. So, the gravitational potential redshift is about a part in 10 to the 18th per centimeter. So we can, just measuring those shifts, we could navigate supposedly down to 1 centimeter scale. And the reason some people find this interesting is basically that people study earthquakes. They know that a precursor of earthquakes is that the strain in the Earth's surface changes. So, for example, if you have 2 different locations separated by about a kilometer, that due to the strains in the Earth, the relative heights of these positions separated by kilometers could change. And anyway, maybe if you can measure those strains precisely, maybe you can help predict when earthquakes will come. So the other thing is, scientists were interested in more fundamental things, and for example, one thing we and other groups have done is if we have 2 clocks and they're based on different atoms, they say mercury and aluminum in our case, the frequency is determined, of course, dominantly by electromagnetic effects. There's also effect of the other forces, weak and strong forces. And so one interesting thing, several labs are doing is just trying to compare clocks based on different atoms. So in our lab, we compared the mercury ion to the cesium clock. And anyway, nobody has seen a shift yet, but certainly a lot of people are looking for this. And the other, popular topic these days is gravity waves, and experiments have been amazingly successful, but there are, by comparing 2 clocks at different locations and comparing their frequencies, that could provide a detection of gravity waves. And also, just on the more fundamental side, we're always looking for deviations from Einstein's theory of relativity. But that hasn't happened yet. So he's still in pretty good shape. So anyway, that's kind of a quick tour through atomic clocks. And of course, these experiments, I showed the group in 1976, and we were only 4 people, and this was the group in the later part of 2018, and at times the group was up to about 30 people. In the meantime, about 15 years ago, we got interested in quantum computers and that sort of thing. And actually, the atoms that are good, for quantum bits also have the same features as atomic clocks. So a lot of the same features. And so, it was easy for us to get into that game. And we at NIST, been playing that game since 1995. So, and anyway, these are the people on the, in the lab doing the work. But I think at NIST, we were also very fortunate to have really great leaders. And, one nice thing is that they didn't determine what they let us determine what physics, we wanted to do. I mean, we couldn't do crazy stuff, but they were very supportive of all the work we did on the clocks, independent of how we did it. So I'm just I think for the students anyway, I don't think I have a very remarkable bringing up, but I'll tell you a little bit about my story getting up to where I am now. And so my parents were, they lived through the Great Depression in the U.S. from about 1930 to 1940, before World War II. And, a lot of people lost their jobs, and it was a very depressed time. And my parents both had college educations, and they had good jobs. And so they weren't affected severely by this. And anyway, but that experience, they certainly, impressed on my sister and I that we had to get good grades in school, so we could get a college degree and find, a good job. And but also, on the more fundamental side, my dad would play, simple math games with me, which first got me interested in math, and later when I was in high school and into physics. And anyway, but even with this emphasis on school, my parents were, very willing to let us explore. And in my own case, I was always saying there were mechanical things. And when I was younger, at late age at 11, I was playing with model airplanes. Anyway, when I got into high school, and my friends and I were all crazy about cars and motorcycles, and so I bought a car when I was 14. And my dad had to drive it home because the driving age, and I was in California, the driving age there is you have to be 16. But anyway, I bought the car, and my dad drove it home, and it had a lot of damage on it. So I spent the next year and a half working on this car to fix it up. And anyway, but it was a good experience, because a lot of the the mechanical things you could do in a lab were just like working on an engine in a car. So it was a really useful experience for me. And I'll just say a little bit about my school. After high school, I went to the University of California, and I went to the Davis campus, which is very close to Sacramento, where I grew up. But Davis was then and was a primarily agricultural school, and it's gotten much broader now. But in the 60s, the place to be for physics in the University of California was Berkeley, which was, just down the road 80 miles. So it was easy to transfer. I mean, I just had to fill out a form and move down to Berkeley to continue there. So that's where I got my undergraduate degree, at Berkeley. And then as I mentioned, I went to graduate school at Harvard. I didn't say that I did a postdoc at University of Washington, and that's where Hans Stamos, one of the inventors of the ion traps, where he was working. I worked on traps, but it was on electron traps when I was there. But a lot of the same ideas came into play, which helped me later. So I think that's about it. Yeah. So anyway, thanks for good, listening, and good luck to all, the students in your career. So anyway, thanks for listening.
Thank you very much, sir. Your words were very, very enlightening. So now we have opened the chat box. The participants can now put in their questions into it. And now I request Bhagyalakshmi and Malavika to read out the questions to Dr. David. Sir, they will read out the questions and you can answer them.
So we have the question here. One of the participants have asked, do atomic clocks slow in electric fields?
Just what was the last? Do atomic clocks do what? Sorry.
Slow in electric fields.
Do they slow electric fields?
Yeah. Do they? Does the atomic clocks work slow in electric fields?
Oh, do they run slower due to the electric fields? Is that what the question is?
Yes, sir.
Well,
Yeah,
I
the
think
presence of electric fields.
Electric fields, they can cause shifts either ways, and we do have to worry about them. The one nice thing about the ion clocks, though, is that because on average the atoms aren't moving, we know that the average electric field is zero. But we still have to worry about second order effects. But the nice thing about atoms, if we can hold them in one place, then we know, because they're not moving overall, then we know that the electric field is zero. So that's one of the nice features about the ions, is they just automatically, as long as we hold them, in one place, then we get away from the electric field shifts. We still have to worry about magnetic fields, which the neutral atoms have to worry about too. So.
We have received another question from the participants. The question is, how long does an atomic clock last?
Well, I don't. I mean, it's more a question of practical things. I mean, in our case where we, are using lasers to excite the atoms, the lasers eventually have to replace. But in principle, there's, if we had lasers that we could switch in, as the older ones got, used up, then in principle we could run it, continuously. But I mean, we don't do that practically speaking. What we typically do, it's a good question, because what we often do is we'll have an array of atomic clocks and we compare them, and we can find their relative rates, and then if one of the atomic clocks has a problem, we can just extract it from the array and then fix it and then put it back in the array. So if we have a network, then we can keep time going without having to worry about one of the clocks failing for some reason.
So we have another question. Quantum entanglements, is it a hypothetical phenomenon or is it real?
Sorry, what? Say the first part again. Sorry.
Quantum entanglements.
Oh, yeah, no, it's very real, and actually, this is one of the. Some of the physics students will know this story, but Einstein was involved in these first ideas about entanglement, and anyway, this is another, to do it right, it's another story, a whole hour lecture. But the basic idea is that this idea of entanglement. One feature is if you have two atoms that are entangled, if in a particular entangled state, for example, you can consider the state if the one atom is measured to be in the excited state, then the other atom has to be in the excited state. And similarly, if the first atom is measured in the lower state, then the other atom is in the lower state. And what Einstein's and people like that theorize, this in principle should happen if you create these entangled atoms and then separating by some arbitrarily large distance. What's interesting is that when you measure one atom, the other atom immediately knows that which state it's going to be in the same state as the other atom. And this almost sounds like something goes faster than the speed of light. And this was what Einstein called spooky action at a distance. And so he was very skeptical there. He thought there was something wrong with quantum mechanics. And in the last 10 years, there's been some really good optics experiments where this idea that widely separated systems can be entangled, and they have this funny correlation which seems to go faster than the speed of light. I mean, that's been proven now without a doubt. So I mean, it's just a very interesting feature of physics that sounds strange, but and in fact it can't be used to communicate faster than the speed of light, but it has this funny correlation which is interesting. So is there any other question or?
Now we have a last question from the participants. Was there any eureka moment during your research which you could say was the Kickstarter of your research on atomic clocks?
No, you have to go slow. I just couldn't make out some of the words.
Was there any eureka moment during your research which you could say was the Kickstarter of your research on atomic clocks?
Which was the what about atomic clocks?
Eureka moment during your research. which you could say was the Kickstarter of your
Oh,
research?
Kickstarter. Okay. Oh, I mean, it was sort of gradual for me. As I mentioned, I got into clocks during my thesis work, and it wasn't just that I liked the idea of time and synchronizing time. It was just a lot of interesting physics that went into this. And the other thing is, I explain about how I worked on my car when I was a young guy, and I just liked working with mechanical things. And so a lot of the clock work involves these mechanical systems that you have to build up. So I think it's just sort of these things came together. And of course the physics is interesting too. And so that was not, I would say there was nothing special that started me into physics. But I always liked it starting in late high school. So
Thank you, sir. That's all from the participants, the questions. Thank you for answering it.
sure.
So now we are moving towards the end of the session. I would like to invite Sudarshan for the vote of thanks. Sudarshan, on to you, please.
Sorry, I just didn't understand. Sorry.
I'm going to deliver the vote of thanks for this event, sir.
Uh-huh.
Yeah, so greetings to everyone present here. I, Sudarshan Muralidharan, am privileged to deliver the vote of thanks for this event. First and foremost, we are deeply thankful to you, Dr. Wineland, for joining us at Tathva 21 to speak on atomic clocks, which are truly a marvel of human engineering. I would also like to thank and congratulate the members of the lecture committee on yet another successful lecture hosted as part of Tathva lectures. We also express our gratitude to our audience for their active participation and for their interest in this topic. Once again, I wish to thank Dr. Wineland for setting aside time from his schedule from this event and sharing with us his extensive knowledge on the working and significance of atomic clocks and his extensive research in the field of atomic physics. We hope we may be able to have you on campus for future editions of Tathva. Once again, thank you everyone for joining us today, and goodbye.
Yeah, well, thanks to you. I mean, it's always a pleasure for me to do this. And as I say, I wish the students good luck in whatever career they choose. So thank you.
Thank you, sir.
Thank you, sir.
Okay.
The participants can now